Hi, everybody. Welcome to this Fiveable AP Physics 1 live stream. Today, we're taking a look at kind of some Q&A about simple harmonic oscillators and just pendulums and springs in general. So this will run probably from till about 8 or until we get to everybody's questions and go from there. If at any time you guys have questions, please just throw them up in the chat. Or click that ask a question button. Either way is going to work just fine. And we'll go through that. The slides for this are linked at Fiveable. So if you want to download those or just have them open, because there are some practice problems we're going to get to eventually. And yeah, so let's get going. And it would help if I find the right screen. There we go. All right. So just as a reminder, if you're taking other AP courses or just want to check out some other streams, at Think Fiveable is our social media for everything. We're doing AP Physics 1 streams, hopefully every Wednesday from now on at 7. I'm doing some. I think Jacob's doing some. I'm not sure who else is filling the other ones, but 7 p.m. Wednesdays, check out Physics at Fiveable. All right, so what's today going to look like? Well, we're going to do basically my 30-second version of simple harmonic motion. And then I basically want to open it up to you guys for Q&A. What questions do you have? Have you covered this already in your classes? Is it something brand new? Anything like that? We'll Q&A for a little bit. We've got some, if you haven't seen this sort of stuff yet, we have some simulations we can go through to explain some concepts. Then we'll dive right into the AP exam, do a few multiple choice sample questions, and finally wrap it up with some free response questions. So that's the plan. Let's see where it goes. So first off, simple harmonic motion. Simple harmonic motion is basically back and forth motion. So a pendulum swinging back and forth, or a spring bouncing, or a mass bouncing up and down on a spring, or basically a kid on a swing set. Anything that has a back and forth motion, but here's the special part. In order for it to be simple harmonic motion, it has to be directly proportional to how far away you are. So on a spring, the more you stretch a spring, the more the force gets, and that's a linear relationship. So a mass on a spring is simple harmonic. A pendulum, as long as you don't pull it back too far, and we can say basically sine theta is the same as theta, you will have simple harmonic motion. If you've done a lab like this, I'm sure that your instructor has said something like, don't pull it back too far because then the period won't make sense. And that's true. A large angle will not have simple harmonic motion, but it'll have some sort of periodic motion in there. And on your reference tables, there are these 3 equations sitting up on the top left corner there. Talking about finding the period. Period capital T, 2 pi over omega. That's more for when we're doing rotational motion, which I think is coming up next in our stream series. I'm not positive about that, though. Or 1 over the frequency. Frequency is how many times per second something happens in there. But the 2 we're really going to hammer on and focus in on are the TS and TP. Period for a spring, mass on a spring to go up and down, and period of a pendulum to go up and down. And those are both equal to 2 pi for the spring. It's square root of m over k, mass over the spring constant. And for a pendulum, 2 pi squared of L over g, that's the length of the pendulum over the acceleration due to gravity. All right. And if you're planning on taking APC or physics at college at some point in the future, there are other simple harmonic motion examples. AP1 just really doesn't concern themselves with anything other than springs and pendulums. All right. So that is my super quick overview of simple harmonic motion. Any questions you guys have about this? Or do you want to dive right into some free response questions or multiple choice questions? Throw up something in the comments and we'll see where we go. Okay, so chat is very quiet right now. So it's okay. We'll go through and let me do a little recap with some of the sims about what's going on before we just jump right into some problem solving sort of this, just so we can illustrate what's going on. So we'll start with the pendulum here, and that should work. There we go. Okay, what was that? So pendulum, basically we've got this wonderful little mass. Why did I say pendulum? Springs, mass on a spring. We've got this idea where we have hanging a mass on a spring makes it oscillate up and down around its equilibrium position, the point where with the weight on it, it would just naturally settle to it. Let's grab this thing. Stop. Let's put you right at the equilibrium position. Okay, fine. And we'll let this go back and forth here. So oscillating up and down, up and down, up and down. If we were to time that from lowest point to highest point, we would get the period of that motion. So about 0.8 seconds here. We've got our natural length of the spring. We got a movable line here. So I'm just going to put that one at the bottom. Looks like about there. And this distance between those lines is going to tell us our amplitude, or half of that distance is going to tell us the amplitude. How far below the equilibrium position did we go? And how far above the equilibrium position did we go? Those two are going to be symmetrical around each other. So for some questions, if you're told, hey, this is the total distance this mass moves, well, then the equilibrium position, the point where everything is balanced force-wise, is halfway in the middle. Okay. We can also look at some energy stuff here. If I hang this mass on here and we'll stretch it a little bit more, we're going to get some elastic potential energy going in here. And I'm going to reset this and turn off the friction since we don't need that right now. Okay, so there is our equilibrium point, and we're oscillating around that. Basically, as we go up, we gain more gravitational potential energy. As we go down, we gain more elastic potential energy because we're stretching that spring. And right at the equilibrium point, right at this zero line right here where the forces are balanced, our kinetic energy is at a maximum. So we go gravitational to kinetic to spring potential to kinetic to gravitational to kinetic, back and forth over and over and over and over again. Okay. The interesting part about this is if I were just to have this run, we'd be able to see that as we go through, try to get is gravitational. Sorry, yes, just gravitational potential energy. I'm going to, yeah, I should say PUG, gravitational potential energy, into elastic potential energy as the spring stretches more and more. So we start with this. I'm just going to get a period here really quick. As we go up, it takes about 0.74 seconds for this thing to happen. But because the period of a spring equation does not depend on gravity, we're going to crank this up and go to some other planet, other place where the acceleration due to gravity is significantly higher. And I'm going to run this. We're going to reset this and see how close we get to 0.74. If this is all working as it should, this should be exactly, okay, 0.69. It should be exactly the same period, regardless of where you are with this. And that's what makes springs really cool, is the period. The time it takes for one complete cycle won't change, whether you're in free fall, whether you're in a different planet, you're on the moon, you're anywhere you want to be. The time that this mass takes to oscillate down and come back up won't change, which is really, really cool. In fact, and leaves itself to make some very interesting clocks and other timing devices and stuff like that. Okay. Other thing we can look at is the forces. Let this go through here. That's really fast. So again, in essence, when we get to this equilibrium position, we have no net force. The equilibrium position where the forces are balanced, the downward gravitational force is canceled out by the upward force of the spring, and they happen to coincide with that equilibrium line. That's where we have the most kinetic energy, the greatest velocity. And then as we go through, we get zero velocity at our extremes, at the bottom and at the top. But interestingly enough, because at the bottom and the top, our forces are the largest they have been, the extremes are where we get the biggest acceleration. And we have no acceleration at our equilibrium point, which is where you have the most velocity. So everything from down here, we're slowing down. Now we're speeding up again. So all that upwards acceleration, we cross over the equilibrium, and that flips to now being downwards acceleration. Back and forth, back and forth, back and forth. And that is simple harmonic motion. The force and the acceleration depend directly on how far the spring is stretched. All right. Questions on springs before we jump to pendulums? Okay, so let me pause the spring one for a second, and we'll switch over to pendulums and do kind of the same deal. Let's see, this to pendulums. There we go. All right, so same basic deal with the pendulum. We take the pendulum, we can pull it back some amount. I'm going to do a small angle because I want to make sure this works right. And we let it go. And we see, look at that pendulum go. Back and forth, back and forth, back and forth. And it period would be the time it takes for it to go back and forth one full cycle. Okay, so if I were to time this, we would go there and off. So about 1.7 seconds for this pendulum to swing back and forth. Now, pendulum ones, the mass of the pendulum doesn't actually matter at all. You could have this be a really small device on there, paperclip, up to a bowling ball, up to a car, up to a whatever. Any object you put on here will take the same amount of time. I should reset that, shouldn't I? To make this progression. So let's just verify 1.73 compared to 1.71. That's my reaction time in there. So yeah, that's the same exact thing. When I went from a mass of roughly 1 kilogram to a mass of 0.1, no real change there. What does change this pendulum period is the length. So here we have two pendulums with the same mass of 1 kilogram, but different lengths. We released them at the same angle, so there's no difference in angle. There's no difference in mass, yet these guys are taking wildly different times to finish because the length of the pendulum is the only factor, only controllable factor that will affect its period. And the other factor that can affect it, although we have no control over it, is the gravity. If I were to take this and put this pendulum on Jupiter, noticeably faster, less than a second for this pendulum to swing back and forth and make its period happen. So more gravity, faster speed. If we go to the moon where there's less, we have a much, much, much greater period on there. So where the spring didn't matter where you were, but cared about the mass on it, a pendulum doesn't care about the mass on it, but definitely cares about where you are, which makes it interesting in that aspect. Okay, talk about energy, because my kids just wrapped up an energy unit. I don't know what you guys are handling, but for this one, it's pretty straightforward. The classic pendulum, potential into kinetic into potential into kinetic. If we had our equilibrium position at the lowest point, just like the spring, this is where you have the most kinetic energy. And at the highest points, you have the most gravitational potential energy in there. So you go from potential energy at the highest point being its maximum, down, changes into kinetic, and then back up into potential, and back and forth, back and forth, back and forth. So that's about it for pendulums. Not much more I can say other than it's just you're doing the same sort of stuff. If you covered energy, all we're really doing with a pendulum is we're tacking on the idea that, oh, the time that it takes to swing back and forth matters on what's going on there. That's not the right screen. Sorry. Let's get the right screen back up here. That's fun. That's better. And close. Okay, so that's basically recapped here. If you get a chance and want to play around more of those sims, they're pretty fun. There's typically a sim on that website, fet.colorado.edu, that will cover pretty much every topic we will do in AP 1, AP 2, AP Chem, AP Physics C, basically tons of simulations on there that let you just play around and have fun with learning about physics stuff. All right, so let's zip in. So let's see here, back to our recap here. We've done SHM Q&A. Jess, any questions you've got about this? Or Rachel, I just saw you pop on. Any questions you guys have? Or do we just want to jump into some AP questions and see how those go? Okay. So if you guys have questions at any time, just throw them up and I will do my best to answer them right away. But since it's pretty quiet, let's just jump right into some multiple choice. Okay. So first one, which of the following is true for a system consisting of a mass oscillating on the end of an ideal spring? So a mass on a spring bouncing up and down, oscillating, oscillating, oscillating. Which one of these four statements do you think is true? All right. So this one, talking about the springs, we saw in the simulation that when we pull the spring down and it oscillates back and forth, the kinetic and potential energies definitely change throughout this, and they are not always equal to each other. So A, not correct. Kinetic and potential energies will be equal to each other at certain points, but they aren't equal to each other all the time. B, no, the kinetic and potential energies definitely change as we go through from potential to kinetic to potential to kinetic. They are not both constant. They are continually changing. All right. C, also, the maximum potential energy is not at the equilibrium position. In fact, potential energy is the biggest at the extremes, not in the middle. So high point, low point will have maximum potential energy, but not the point right in the middle. That will not be a maximum potential. That will be the maximum kinetic. So process of elimination, choice D is the right answer here. The biggest kinetic energy and the biggest potential energy are equal to each other? Yes. At the highest point and lowest point, we have maximum potential energy. And then at the equilibrium point, we have maximum kinetic energy. Those amounts are equal to each other, but at different positions. Right, next question. When an object oscillating in simple harmonic motion is at its maximum displacement, what's true of its speed and restoring force? Restoring force wouldn't be acceleration. It'll be the net force. Although if you know what the acceleration is, the force would also do the same thing on there. So if we're looking at this question, first thing I would ask myself is the farthest point from the equilibrium position, so the farthest point away, are we moving at that point? And let me pull up the spring again, just to illustrate that. Stop sharing that, pull up the spring. There's got to be an easier way to do this, but that's okay. Springs, okay. So if we're looking at the spring one, when we are at our maximum distance from equilibrium, so either the highest point or the lowest point, our velocity, our green arrow, stops. All right, when we are up at our highest point, we are not moving at all. So the restoring force, this net force right here, which is gravity and spring, gravity pulling down, spring pulling down, this gives us the biggest possible net force at that point. And Jess, you mentioned acceleration. Because F equals ma, the force, when it's biggest, will also have the biggest acceleration. So if you remember, acceleration is the biggest at the extremes, force is the biggest at the extremes as well. Okay, so this one has the most acceleration, the most force at the extremes, and the smallest velocity at that extreme. All right, so the correct answer will be whichever one actually has that. But if I pull up the slides again, you can take a look. There you go. So this one should be choice A. We aren't moving at the extremes, but we do have the maximum force going on there. All right. Next one. How does the velocity change velocity? Okay, so hold on a second. Let me go back to your question there, Jess. Let me get back to this one. So in this case, we're just going to turn, I got to turn off the dock, turn on the simulation. Maybe that'll be easier. Just do this. Is that any better? Yeah, that might be easier. Okay, we'll see if this works. So in this case, the velocity is the green arrow on this sim. So I'm just going to let it go here. So as this oscillates up and down, we start with the velocity at 0 when you pull this down. Then it gets to its maximum value right at this equilibrium position, right at this dashed line. Then it slows down, slows down, slows down, hits 0 at the top again, and reverses. So if you were to graph this velocity, it looks like a sine wave. I don't think I have the capability to do that in here. Maybe I do. No, I don't. Rats. The graph of this would look very much like a sine wave, up and down and up and down and up and down, which is where the connection between this and waves comes in. So if you were to look at the velocity, it looks like a sine wave. The acceleration looks like a cosine wave. And basically, we'll just repeat forever and ever and ever. All right. Yeah, I wish there's a way I could show you that, but I don't have anything set up to show that part of it. But basically, highest, change direction, 0, negative, most negative, 0, most, that sort of thing. So around, up and down, up and down, up and down, up and down, like a wave that you would imagine looks like. All right, does that help? Maximum velocity at equilibrium, 0 velocity at the extremes. Let me see if I can find a little thing here. Let me do a little Googling quickly here for you. See what I can pull up that helps here. Okay, yeah, this might work. Come on, load. Okay, so here's a different version of, I don't know what that noise was. That's interesting. We're gonna just mute that slide. Okay, so basically here we've got this spring going up and down, and its position graph, how high above the ground it is, looks like a sine wave. Okay, if we do the same thing, this one we've got our velocity, also looks like a wave tracking through, and the acceleration looks like the same exact thing, just shifted a bit. So this is where we get wave parts. So we start coming down, we're at our highest point, our velocity stops right there. So there is the maximum value at this point. Our height is at its highest point above equilibrium. Our velocity is 0 because we've stopped, and our acceleration is super big, pointing down. We then step through a little bit, and right about here, we reach the equilibrium position, where our height is roughly right around the middle. Our velocity is at its biggest point going downward, so our speed's a maximum, and our acceleration is pretty much 0. Okay, that's because at this point, this halfway down point, there is no net force. The up force and the down force from the spring and from gravity cancel each other out. So there's no acceleration, maximum or largest speed, largest negative velocity. And then we continue onwards. We get to this point. This is the furthest down we reach. Okay, our height is at its lowest, our most negative point there. Our velocity is at 0 because we come to a stop again. And our acceleration is again at its largest value, except for now it's pointing up to pull the mass back upwards instead of pulling it downwards. And then this will just repeat itself. We get to the equilibrium position. We have our velocity being its highest point, this time going up instead of going down because we've changed direction, but this would be maximum velocity. At that point, no acceleration. There's nothing there because the forces are all balanced. And yeah, we're at our equilibrium position. Then we continue onwards, get up to the top again, and we're back to where we started. Maximum height, no velocity, downward maximum acceleration. And then continue onwards, equilibrium point, lowest point, equilibrium point, and then we repeat. All right. Does that help? Okay, good. Okay, so let's put that one away. Let's try the next question. All right, so this is our last multiple choice one that I found. So we have a pendulum and a mass and a spring. Both have a period of 1 second. So they both take 1 second to go down and come back up. And that's when they timed it on Earth. They then, some astronaut takes these things to planet X, which has the same diameter, but twice the mass. So same size as Earth, but more massive. Which is true about the periods of these two objects on planet X compared to the periods on Earth. right, so for this one, we're going to look at our two basic equations for simple harmonic motion. We've got a spring and we've got a pendulum. The spring, well, the time the spring takes to make a complete oscillation depends on the mass on the spring and the spring constant. In this example, we didn't actually change either of those things. We changed the mass of the planet, but the spring is still the same spring with the same mass hanging on it. So this means for the spring that nothing changes. Okay? So that means that we can rule out choice A because the spring doesn't care about being on a different planet. Okay? And I'm going to rule out C too because the period of the spring doesn't change. So A and C are both wrong because the spring doesn't change because it only cares about the mass on the spring and the spring constant. There. All right, so now let's look at the pendulum. So the spring, or what are we down to? We're down to B, both of them don't change, or D, the pendulum changes, but the spring does not. All right, so the pendulum depends on two things. The length of the rope, which I don't think we changed the length of the pendulum in this question. It's still the same pendulum. Nothing in this paragraph says we changed that, made it longer or shorter. So L didn't change, but what did change is little g. On a more massive planet, in fact, this equation, more massive planet means bigger force of gravity. Bigger force of gravity means bigger acceleration due to gravity, which means this little g just got bigger. It changed. And if that gets bigger, this whole fraction gets smaller, which means the pendulum actually gets a shorter period because it's on a place with more gravitational force or more acceleration due to gravity. All right, so the correct answer here is D. The spring doesn't care where it is. We didn't change the mass. We didn't change the spring constant. But the pendulum, because we changed the acceleration due to gravity, because different planet, we will end up with a shorter period because gravity was higher. So, how we doing? Any other questions on multiple choice, springs, pendulums, stuff like that? Or do we just jump right into some free response and see how those go? So mechanical energy, potential plus kinetic. Yeah, for all these, the total energy, I shouldn't say that, as long as there are no outside forces. So there's no friction. There's no, friction. Yes, the total energy for both the pendulum and for the spring remains constant through this entire process. So again, as long as we don't have any friction, yes, total energy, mechanical energy will remain constant. I like all right. So there's quite a few free responses we can do. I think I'm going to start with this one, just because this one kind of walks us through all the basic parts that you could be asked to do with a pendulum. So, and then we'll get through this. I don't know if we're going to have time to go through the other ones, but if not, I can always quickly jot down answers. And then as you watch replays and stuff like that, we can go through and check that. All right, so we're going to work on this question. This is off a old exam I gave. And yeah, let's solve this. So let me switch over to my document cam in a second here. Why don't I have the ability to close? Where's my close video? Unfocused screen. Unfocused screen. There we go. Okay. Sorry, I am trying to get used to this. And boom, there we go. Okay. So here's the question we have to work with. A simple pendulum has a bob with a mass of 0.85 kilograms attached to a string with a length of 1.5 meters. We pull it back to point Q, and then we let it go. So it swings back and forth between P and Q, P and Q, P and Q. Right. So on the figure below, draw a Freebody diagram showing and labeling the forces acting on the bob in each of the positions described. All right, when it's at point P and when it's at the lowest point in its motion. All right, so let's start off. There's point P. I know normally you'll have space to work. This is crunched for space. So we're going to pretend that this dot is point P and that's the ball. How many forces are going to act on the ball at point P? Focus is better here. And it's not focused either. All right. So at this point, point P, we have two forces going on. We've got tension, which is pulling the string, pulling the ball back up towards the top. And we have gravity, which is pulling the ball straight down. Okay? Two forces on there. And I'm going to see why this is not focusing well here. My apologies. There's just a lot of noise in there. Find something to focus on. We got it. Make it work. All right, this is going to die for a second. Really annoying. On there at the bottom of the loop there, we have again two forces going on, where you have tension again pulling up and gravity pulling down. Let's see if this works. Refresh. Yeah, that looks a bit better. Still not great. Better. Okay. So at the bottom point here, that point, we've got gravity going down and tension pulling up. So those two forces are now in opposition of each other because tension's pulling up, gravity's down, unlike this part where they're working generally in the same direction. All right, part B, calculate the speed of the bob at its lowest position. All right, we're looking at speed, velocity. There's two things I'm thinking. This could be a forces question since they just had us do stuff about forces. It's a possibility that we could do something like sum of the forces equals MA, and then tension minus the weight equals mv squared over r. The only problem with this is I know the mass, so I can find mg. I know r, but we don't know what tension is. So this one could work if I knew what t was, but I don't. So we're kind of stuck through trying to figure out another way to do it. This, actually, if I was smart, and you should be smart, read ahead and say, hey, we're trying to find the tension in part C. which means this is probably what we're doing for part C up there with the forces and stuff like that. To do part B then, the only other thing we can do is talk about energy. How at the beginning, at point P, we have all potential energy due to gravity, and at the bottom, it all turns into kinetic energy. So we can say something like potential turns into kinetic, mg delta H equals 1/2 mv squared. We get to drop off our m's because that's a good thing to do. Simplify a little bit. And let's multiply by 2 as well. So 2g delta H equals v squared. And then we can go through and figure out the last part. So if we're doing this, 2 times 10 times 0.08 equals v squared. 2 times 0.08, 2 times 0.8, 1.6 equals v squared. And that means v is the square root of 1.6, which then we can grab on a calculator and say this is approximately 1.3 meters per second. All right. So part B, fairly typical for a pendulum. If you have a pendulum question show up on the exam, there's going to be part of it about energy, just because that's how it works normally. Okay. Does that part make sense? Okay. So then moving on to part C, we're looking for the tension in the string. Well, I kind of already started that when I was trying to figure out how to do part B. So in this case, we're looking for the tension. Tension must equal mg plus mv squared over r. And now it just becomes some adding process here. So m 0.085, which we found before. So this is 0.085 kilograms times 10 meters per second squared plus 0.085 times 1.6 squared. No, sorry, it's already squared. Square root of 1.6 squared is 1.6 divided by 1.5. Put all that in the calculator. It will tell you the tension is roughly 0.93 newtons, give or take. And again, you get a little bit of leeway depending on rounding, depending on whether you use G as 10 or G as 9.8. I always use 10 and have my kids always use 10. It just makes the math easier on there. But this is why you get a calculator on the exam as well to crunch those numbers. All right, now the actual part of this question that pertains to what we've been talking about is part D. How could you change this pendulum to double the period? Okay, so for this part, and this would be a great qualitative, quantitative example for free response, or a justify in a paragraph, or a derive the equation and then explain why it works sort of section in there. But the period of a pendulum is 2 pi square root of L over G. And if I want to make this period become 4 times bigger, sorry, double, 2 times bigger, I have choices. I can either change pi, which is not going to happen because that's a constant, or I can change L, or I can change G. And since I'm not getting rid of pi at all, that's stuck there. I can't really change that. Either I can have the square root of L nu, be equal to 2. Boy, I'm really bad at this. So the square root of L can be 2, or the square root of 1 over g can be equal to 2, because doing either one of these two things will double the period. Well, in order to make the length, square root of the length be 2, I need to make the length get 4 times bigger, because the square root of 4 is 2. Likewise, I could do the same with the acceleration due to gravity and make this be 1/4 as much, because 1 over 1 over 4 is 4, and the square root of 4 is 2. So in this case, we kind of have two options. One's easy. Let's make the string 4 times longer. So 4 times 1.5 makes this 6 meters instead of the 1.5 meters it started with. Or I go find some place in the world or off the world where the acceleration due to gravity is now 1/4 as much as it was already. So 10 over 4 or 2.5 meters per second squared. Those are my two options for making this pendulum have twice the period. By far the better option, especially if this was a lab sort of thing where you had to vary it or something like that. So definitely I would look at making the pendulum longer instead of not. All right, I think we got time for one more. So we just did a pendulum one. Let's look at a spring one. Okay, so on the spring one, we are going to look at this sample one. So a spring with a spring constant is hung vertically from the surface, and block M is on there. We let it go, and we release it and let it come to equilibrium as shown in the diagram on the right. So right here, we are at our equilibrium position. This is a bit clearer on the slides than in my poor photocopy here. But this is our equilibrium position right there. Derive an expression for the equilibrium position of this mass. Okay, so equilibrium position means that all my forces must be equal. So that means that the force on a spring going up must be equal to the weight of the block going down. So I would set up and say the force on a spring is equal to the weight. Force on a spring, right off your reference tables, is K times X equals the weight. And our job here is to find that distance, that X. So we can simply say I'm going to make it a Y because we're talking vertical, not horizontal. Y will equal mg over K. And there we go. That is our equilibrium height setup. Okay, forces must be equal up and down. Okay. Part B says the spring now gets pulled down a distance A. Derive an expression for the potential energy stored in the spring. All right, potential energy is 1/2 kx squared, and x is the distance from equilibrium, which in our case, they tell us in this question that we move a distance a. So our potential energy must be 1/2 k a squared. All right. So far, this one's pretty simple. We did a little forces equation. We've plugged in stuff for potential energy. Part C, we want the expression for the period of the spring. This is right off the reference tables. Spring 2 pi square root of m over k. Okay, and now we get into the meat of this question, because B and C were pretty much just look on the reference table and find something. Part D, describe a procedure that you could use to verify that this actually tells us the period of the pendulum. Include all equipment required. So in this case, really what we're going to do is we can grab our handy dandy lab tools, and I need to basically measure one thing, and that's the time it takes to go up and down, and just to see if they are equal to each other. So I have a theoretical, but realistically, all I would need to do is have a stopwatch, and I want to time how long it takes to go down and come up. Now, because we want to do this as a good experiment and not just a one-off, what I'll probably do is time maybe 10 cycles and then find the average. And then that will tell me the period. You could also, if you wanted to, get a little bit more fancy and be able to, let's say, time different masses on there. And then you'd be able to go through and, let's say I changed 5 or 6 different masses on there with the same spring. Then I'd be able to do something like find and make a graph of period and square root of the mass. I'm doing square root of the mass because it's square rooted up here. And this will put it and give me a linear graph. If that's linear, we're good. Okay. So this should be linear if the period and mass actually hold up. My spring's ideal. And I'm kind of getting ahead of myself here, but that's part E. So I would, again, get the times. We'll do that for 5 different masses. And then be able to plot period versus square root of the mass. And this will look something like this. So there's my equation, and I plot this on the y-axis, and I plot square root of m as my x-axis. That means whatever's left over, the slope of that line should be 2 pi over the square root of k on there, which, again, this would be one way for me to verify if this was actually right, if I went through and calculated my slope and found that out. Depending on whether you like doing square roots or not, you could also have done something like your graph could be period squared versus mass. And then the slope here would be 4 pi squared over k. And that also would give you the same exact result. Same basic idea, just square everything before we figured out what was what in there. And that's probably the best way of doing it, either t and square root of m or t squared and m. The AP exam, if you're given a chance to make a graph and use a graph to show and justify your answer, experimental questions, definitely go that way if you get an option. So instead of saying, oh, I would just find the average and see if it matches up, that's good, and that would work. But really, the AP scorers and rating guides really want to do stuff with graphs and more graphs and more graphs. Linearize that slope, see how it works, and go from there. All right, so that was kind of an overview of springs and pendulums. Jess, any other questions, or are we good to sign off? All right. Thank you. All right. Have a great night, everybody. And again, next week, Wednesday, 7 o'clock, we'll move on to our next stream, which I think is rotational motion of some sort. But feel free to check back then. Have a great night.